Wanted to show you my world famous yo-yo trick, the floating yo-yo. So the floating yo-yo is basically, I'm going to release this yo-yo from rest and it will not approach the floor. It will just float right in front of your eyes, and of course to do that we need to pull up with our hand. Well, that wasn't so amazing. That is because it's hard to pull up with a constant force. The other problem is the radius that the string is wrapped around changes as it unwinds. And so the angular acceleration of the yo-yo is not constant. So that makes it even harder to pull up with a force equal to the weight of the yo-yo. So to get around these problems, well, I created a yo-yo just for this trick. It's really just a spool used to store cable, so speaker wire or something like that. Go to the hardware store and you'll see all kinds of ones like this. You may even have some around your physics equipment room, because these are good for other demos where you pull it with the string. I used to use a much smaller one than this and it works just fine, but as time went on it was, go big or go home, so I use this one. And the advantage of it is if I wind the string around it, the radius doesn't really change. And to get around the pulling up with my hand problem, the string goes up and over a pulley and then it's attached to a weight, so I get a constant force pulling on it. And so I turn the problem into how much weight should I put on the end so that the yo-yo floats. So here's a close-up of my setup. So I have a pulley on the ceiling. I have a strong magnet that attaches it to the ceiling. You'll see that maybe that's not the best idea, but it can be made to work. And so if you can securely attach the pulley, it might be better. And then I have the string going up and over it. One end is tied to the giant yo-yo, and you can see I have it taped so it doesn't slip. And so you can just tie it tighter, but that tape seems to work. And then the string goes all the way down, and then there's the unknown mass we'll be solving for. And I have it land on a cushion. I usually try and catch it before it lands, but I don't always, and so that keeps it from exploding when it hits. And I have a pretty good nylon string there. You want something pretty sturdy if you're going for a big one. But again, you don't need that large a one. Whatever spool you have on hand is fine for doing the floating yo-yo trick. So here's the analysis for the floating yo-yo. I won't go into all the details. You're a physics teacher, you can work this out. I am doing this for an AP Physics Mechanics C class, so it is a fairly advanced rotational dynamics problem. And so here's a sketch of the setup. I'm calling big M the falling mass that's are unknown, and then this would be the yo-yo. And we know some things about the yo-yo. We know it's rotational inertia. I figured that out by putting it on top of a rotating disc that was spun by a falling mass. This is a lab we do in my class, and calculated the rotational inertia of the disc yo-yo combination, and then I did it without the yo-yo and got the difference. And so just determining the rotational inertia of the yo-yo could be your unknown too. Find what mass makes it float and then solve for I. I think it's more fun to figure out what I is ahead of time on your own and then use it as a given, solve for the unknown mass. And then we know the mass of the yo-yo, and then the radius of the yo-yo is not the whole size of it, it is just the radius of the axle. So we're not using really the dimension of the yo-yo. And so free body diagram of the yo-yo and some of the forces. The key thing is the acceleration of the yo-yo will be 0 if we're successful. So you know the tension equals the weight. And then some of the torques equal I alpha. And so the torque is from the tension if we're summing about the center. And then I is a given. And then alpha is the acceleration over the radius. And then solve that for the acceleration and substitute it into here. Then you have some fun algebra to do. The key thing is to know what your unknown is. Sounds like Donald Rumsfeld there. So my unknown is big M, so I gather my big M terms. the G cancels, and then I can factor big M out, and then I get this. You could divide through by little m. You could do other things if you want. I just left it like that. You can see the units come out to kilograms because I have an mr squared, which is the same units of rotational inertia. So the denominator is dimensionless, so it's going to be in kilograms, and I get 0.78. Then we're going to test it. Now we are neglecting the rotational inertia of this pulley, and so I added 5 grams to the unknown just after I tried it out. There was a little motion that seemed to work well, but still pretty much using what we solved for. So let's see how it works. So I'm going to show you what it looks like in real time, and you're just going to see up here, and then I have a clip that shows it in slow-mo that shows more of the whole thing. And so I carefully wind it up so the string stays in the middle. So have something to say when you're doing this in class. I let my students film this, and so usually this time gives them a chance to get their phones out and set it in slow-mo if they want. Regular looks good. And pretty much got it there. And so carefully release it, and then I usually try and grab it as the mass hits the ground. We'll see how successful I am at this. And so you can see the pulley came off, but wasn't really a disaster. It's all ready to go for next class. And stay tuned and see the slow-mo that also doesn't quite work out well. So give this a try. It is the world's greatest yo-yo trick.